The exercise, the assignment related to the electrode potential and transition metal, as the two topics are related to each other. And I did the first 9 questions from this. So starting with question 10. In question 10, a yellow crystalline solid E was dissolved in a distilled water to give a yellow solution. Addition of a dilute sulfuric acid to this solution produce an orange solution. So normally when we have a dichromate, it changes its color in acidic and alkaline medium. When we warm F with basically ethanol will be oxidized to carboxylic acid and it will reduce the substance. Here, when we have chromate ion, Cr2O7, turn into CrO4 with the charge, because chromium is +6, so this is -2 here, and this will be -2 as well. When we write a balance redox equation, we need 3 water molecule because 7, and before writing the water molecule, chromium is balanced. So here we should have, to balance oxygen, we add water, so we'll add water here, and then we'll add, to balance hydrogen, we add protons, so 2 protons are here, and then the charge will be balanced as well. Oh, like electrons, we'll add 2. Here we have -2, here we have so we'll add electron here. But the idea is that what will happen if we add an acid, if it is in acidic condition? Acids have more protons, so equilibrium, the balance will shift toward the left hand side. So, and an opposite will happen if we add an alkali, the equilibrium will shift towards the right hand side. That's why the color changes happen. If we warm this chromate ion or dichromate ion, which is in chromium 6 is there, when we warm with ethanol, ethanol will oxidize to carboxylic acid, ethanoic acid, and it will reduce. That's why the solution turned green. The standard cell was set up using the solution F and G for the right hand electrode and ethanol on the left hand electrode. And the cell voltage was 1.94. So voltage which the cell produced, that is 1.94. Deduce the formula of the ions responsible for the color of F and G, and using the standard electrode potential and the electrode potential of a cell, and use the value in the data booklet. So we need a data booklet for especially the electrode potential questions. You have to use a data booklet. So as they already mentioned, they specify that the standard cell was set. So whenever they mention like standard cell is set up, and their positions are also mentioned. Like on the right hand electrode, we have solution of F and G. On the left, we have ethanol and ethanol. So what is the equation whenever standard cell is set up? The standard electrode potential equals to electrode potential of the right hand side minus the electrode potential on the left hand side. This is whenever standard cell is set up. Or it is always oxidation minus reduction. You can also use that. Just remember from redox. Sorry, reduction minus oxidation, because redox is there. So you just do reduction minus oxidation. You will also get the cell voltage. So both ways we will get the same answer. So first what we'll do, we'll work out the electrode potential and of this solution, and then we'll compare what we have the solution. So you can use any of them for any of the formula. So this is minus 0.61 volts. And on the right hand side, we have this. So this is unknown X is there minus. On the left hand side, it was 1.94. On the left hand side, it was, yeah, electrode potential of a cell found to be. So this was 1.94, sorry. And the voltage of this ethanol to aldehyde, or ethanol to ethanol, was minus 0.61. So the cell voltage was 1.94, and the voltage here is minus 0.61. So you just simplify, like minus minus plus, it will go other side, it will be negative again. So we just subtract, so we'll get as 1.33 volts. So that is X. Or you can also use this reduction minus oxidation. So what is the reduction? Like chromium is actually, it's a chromium, it is reduced, so that is unknown. Oxidation, alcohol oxidized to aldehyde, so that voltage is minus 0.61, and the cell voltage was 1.94. So again we solve, we'll get the same answer. It won't make difference if you use reduction minus oxidation or you will use the electrode potential on the right hand side cell minus electrode potential on the left hand side cell. Then we have to identify the F and G. So for that, we will use the data booklet. We want like chromium, and that is 1.33. So conversion of a chromium and dichromate. So you can see here, this one, 1.33. And in which it means this is actually green in color. So what is the other ion? That is Cr2O7. That was originally in the question they specify that we have an orange solution. So that is actually the orange solution. So this is the orange solution because of the ion here, and the chromium plus 3 is green. Is it clear how we worked out? So first we work out the electrode potential, and from electrode potential we work out what will the charge or what are the ions. Basically there will be two ions. One is Cr2O7, another one is Cr plus 3, and we know Cr plus 3 is actually green in color, so this was green, and this one is orange in color. And this one, CrO4, that will be yellow in color. So in the next question, write the overall equation. Write the overall equation for a reaction in a cell, and state symbols are not required. So how you can write an overall equation? Look, when we work out for the chromate, this was the equation Cr2O7, 14, then 2 chromium and 7H2O. That was the equation. And these electrode potentials are always written for reduction, like to gain electron. So it is Cr2O7 plus 14 protons are there, will give 2 Cr plus 3 plus 7 water molecules are there, and the number of the electrons in this system, as the overall charge, because here when we check the overall charge, these are the 14 and this was minus 2, so there is plus 12. And when we write the overall charge here, this is plus 6. So we need 6 more because we want to balance the left hand side. So here it is plus 12. Here we have plus 6. So we can reduce here by adding 6 more electrons. So that is how we reduce. Now, to write a balance equation, what we can do, there are two ways to write this equation. Like we want to write a combined equation for this. So you can do like reduction minus oxidation, and the electrode potential for this change is 1.33. So the one which is positive, it means it gain electrons. So the reduction happened. It means oxidation is happening for the other one, because the one which is more positive or higher positive, that reduction happened. So first what we do, we make the number of the electrons same for both equation. So how to make, there are 6 electrons here, so we want to make 6, so we multiply this by 3. So this will be 3, this will be 6, 6 and 3. No need to change the electrode potential because that is a standard electrode potential. It's for like 1 mole that you don't have to change. We don't want the cell voltage. We just want the equation. So for reduction, you will write as it is. But for oxidation, write it opposite because all equations, the electrode potential equations all are given for reduction. So oxidation one we write as it is, but reduction one we write opposite. Like the one which is a product for it, we'll write as a reactant. So it will be 3C2H5OH, and then this will be the, what is the reactant will be a product. So C3H7CHO, the aldehyde, plus 6 protons are there, plus 6 electron. And now we combine the two equations because the question is write the overall equation. So when we combine, so electron always cancel with electron because electron number always cancel out each other. So electron now, so what we are left with in this overall equation. So in this overall equation, we are left with Cr2O7 with the charge -2 plus 3C2H5OH. There are 14 here and there are 6. So we like 14 minus 6, that will be 8. So there will be 8 protons because here we have 14 and here we have 6. Then about the product, so it will be 2 Cr plus 3 plus 3 CH3CHO, the ethanol, plus 7 water molecule. So this is a combined equation or overall equation. So idea is that whenever you have electrode potential given, you identify which one is having a higher value because it's always the reduction minus the oxidation. So we write the reduction equation as it is, and first we make the number of electrons same. Reduction equation we write as it is, what are reactant product. But for oxidation equation, like in which oxidation happen, as we write the reactant as a product and the product as a reactant and add the two equation, then write in a simplified form. So this is the overall equation for this reaction. Then write an ionic equation for a reaction of aqueous solution of E with dilute sulfuric acid. State symbols are not required. So what will be the ionic equation? It's basically, after writing an overall equation, it's ionic equation. So first we have Cr O4 with a charge -2. It has turned into Cr2O7 with a charge -2. So 2, this should be balanced. Then to add, like what we have to do to balance the oxygen, we add water. So here we have 7, here we have 8, so we should add water here. So we add 1 water molecule, H2O. To balance the hydrogen, we add proton, so we will add proton. But this is ionic equation, and so we don't have to mention like electrons here, as it's not a redox equation, just an ionic equation. Is it clear, this one? Is a conversion of the solution E to F. Like the ionic equation for reaction of aqueous solution of E with sulfuric acid. So E was converted into F. And this was actually yellow in color. And this is orange in color. In question 11, compare and contrast the mechanism of action of platinum as a catalyst in the removal of pollutant from a car engine exhaust fume with that of vanadium 5 oxide as a catalyst in a contact process for manufacture of sulfuric acid. Journal definition of catalysts are not required. So you just want to compare. You're using two catalysts first. The type of the catalyst, because the catalyst can be a homogeneous or catalyst can be a heterogeneous. So if it's a homogeneous catalyst, it means they should have the same state as the reactant. But when we are like using a platinum in a catalytical converter, or we use vanadium pentoxide in a contact process. Vanadium pentoxide or platinum both are solid, but the reactants here, like example, nitrogen monoxide and carbon monoxide are gas, same as contact process, sulfur dioxide and oxygen both are gas. So it means the first thing, in both cases, the catalysts are heterogeneous catalysts. Means the state of a catalyst is not same as the state of the reactant. They have different states. That is one thing. Then how these catalysts work, how the basically here you have to explain how heterogeneous catalysts work. So what heterogeneous catalysts will do, they will trap the, or they will absorb the reactant on the surface, and as a result, when they absorb, they weaken the bond in the reactant. So when they weaken the bond, and second thing, they increase the surface area as well. Like if this was a catalyst, so they trap the reactant particles on the surface. So as they trap the as they trap the water part, the reactant particles on the surface, so two things happen. Like within the reactant particle, there are bonds. These bonds become weaker. That is one thing. The second thing, it increases the surface area, because in a gaseous state, the particles are moving randomly. There is no specific position. So as a result of a heterogeneous catalyst, they absorb the points which you will always mention to score the marks. First is identifying type of a catalyst, because homogeneous catalysts, how they work, they can be easily oxidized and reduced. So first they will be like oxidized, then reduced, or first they are reduced, then oxidized. But overall, because the overall it does not change, that's why we say they are catalysts. But heterogeneous, they absorb the reactant particle. On the surface, and when they absorb the reactant particles on the surface, what will be the advantage of this? They reduce the bonds, bond like weaken the bond or reduce the bond strength, which lower the activation energy. Like the same reaction can occur at a low temperature. And what else? They increase the surface area of the reaction for the reaction to occur. So these are the points you will mention. Like both platinum and vanadium pentoxide are the heterogeneous catalyst. And in heterogeneous catalyst, what will happen? The reactant absorb on the surface, which weaken the bond, it increases the surface area, lower the activation energy. And in case of vanadium oxide, like what can happen? Vanadium pentoxide, so it's a pentoxide, so it's like V's plus 5. So it can reduce and oxidize. So vanadium can be, because it has a pent or a vanadium 5 is there, which can be reduced and oxidized in contact process. Another question from the electrode potential, question 12. The reaction between iron 2 ion and manganese 7 ions are investigated by setting up a cell. So you can see this cell is there, in which iron 2 has converted into iron 3 and MnO4 with a charge plus 7 turned into M. So this is oxidized, the other one is reduced. A solution A contain both iron 2 and iron. Identify the substances used for electrode. Look, as you can see that there is only change in the valency or the charge. So we don't need this electrode made up of iron. So this electrode should be made up of platinum, Pt, and like inert material. Same thing, MnO4 aqueous turned into Mn plus 2 also aqueous. So again, there is a change in oxidation number, but it's not like forming the iron. It's not forming a manganese metal. That's why this electrode should also made up of platinum. What if the question was like in this one, iron solid was turning into iron 3. In that case, we need the electrode made from iron or an iron turned into a metal. But in both cases, because there's only change in oxidation number, it does not form a metal atom. That's why the electrode should be made from platinum. Both should be platinum. So X and Y, both electrodes made from platinum. A student suggests that for a standard condition, solution A should made from mixing equal mole of 1 mole per dm cube iron sulfate and 1. This mixture is not suitable. Why? Because whenever we say we need a electrode potential, a standard electrode potential, we should have a concentration 1 mole per dm cube. If you check iron 3 sulfate, if student is mixing like iron 2 sulfate will dissociate into 1 iron ion and 1 sulfate ion. So if student is taking 1 mole, you will get 1 mole of this and 1 mole of, so that is correct. But what about iron 3 sulfate? In iron 3 sulfate, the formula will be Fe2SO4 in a bracket 3. So when it will dissociate into ions, it will dissociate into 3 ions and it will dissociate into 2 iron 3 ions and 3 sulfate ions. So if I take 1 mole per dm cube, the concentration of iron 3 won't be 1 mole, it will be 2 mole per dm cube. So it won't be standard, because to make a standard solution, we should have 1 mole per dm cube of each ion. So what should be the concentration we should take for making it standard? We should take as 0.5 mole per decimeter cube. So when we take 0.5 moles per decimeter cube, this will be 1 mole per dm cube. So state how this mixture should be changed and justify your answer. So you will simply mention like 1 mole of iron 3 sulfate gives 2 moles of iron ion. So if we take 1 mole per dm cube, the concentration will be 2. But that's why we should take 0.5 mole per dm cube of iron 3 sulfate to give 1 mole per dm cube. Because in a standard condition, it should be 1 mole per dm cube. Identify the compound that may be used to make solution B. So we want to make solution B. We want KMnO4 and a manganese. So what we should mix, like we want manganese 2 also, and we want manganese Mn plus 7 also. So which compound? Mn is plus 7. So that is KMnO4. So identify, so it should be mixture of KMnO4 and manganese, because it should be a soluble, all nitrates are soluble. So manganese 2 nitrate. So it should be a mixture of these two. Why? Because this will provide Mn plus 7 ion or MnO4 ion, you can say, and this will provide Mn plus 2 ion. A student suggested that the salt bridge could be made by soaking a strip of a filter paper in barium nitrate. The reaction occurs when the salt bridge become in contact with iron 2 sulfate and solution A. State what observation would made and write an ionic equation. If a salt bridge is made up of barium nitrate, so barium will combine with sulfate ion to form barium sulfate. Normally, we use group 1 nitrate salts, so they are all soluble. If this was barium nitrate, Ba is there and NO3. And there is a sulfate ion. So this sulfate ion will combine with a barium ion, and as a result, barium sulfate is a white precipitate. So what will be the observation when this reaction will happen or occur? So it will give us a white precipitate, and then we have to write an ionic equation for that. So ionic equation, the barium ion combined with the sulfate ion, and don't forget to mention the state symbols, it will form barium sulfate. That is solid. Suggest some more suitable compound to use when making a salt bridge. So always remember, whenever you want a substance to be a salt bridge, it should always be like a group 1 nitrate, or usually like potassium or a sodium nitrate. So we'll use a potassium nitrate or a sodium nitrate. The electrode potential for us, we want to calculate electrode potential of a cell and use the data on page 17. A data booklet, page 17, we will use. And what are the reagents for us? This is basically, we want the electrode potential for iron 2 and iron 3, and we want Mn4 to Mn7. So data booklet, page 17. This one is 14. Yeah, this one is 17. So what we have iron 2 and iron 3. We'll find what is the electrode potential for that. So you can see here an Mn. So we have this one, iron 2 and iron 3, and we have MnO4 and Mn plus 2 is there. So this one, because MnO4, this one is also there, but that is manganese 4 oxide. That is solid, but we have aqueous. That's why we select this one. Why I did not select for iron this equation? Because here iron solid is formed, but we have the iron solid is not formed. Here we have iron 2 and iron 3. Now you can see two electrode potentials are there. One is 0.77, another one is 1.51 positive. So which is a higher value, for that reduction happen, and which is a smaller value, this oxidation happen. And how we work out the electrode potential of a cell? So electrode potential of a cell, just remember redox means reduction minus oxidation. So reduction was 1.51 minus oxidation is 0.77. So this will give us the standard electrode potential of a cell. So it will be 1.51 minus 0.77. That is equals to electrode potential of a cell will be 0.74 volts. And better write positive, because a positive sign of electrode potential cell shows means it will have a higher entropy, or like entropy increases, or this reaction is feasible. So that was how we work out the. Then in part B, 3 grams of powdered hematite which contain iron 3 oxide, only iron compound dissolved in a sulfuric acid. The iron 3 was reduced to iron 2 using a solution of sulfur dioxide. The resulting solution we make to 250 cm cube, and we just took out 25 cm cube and we titrated with manganate. So we have the volume and concentration. Explain why the solution of sulfur dioxide is suitable for reducing iron 3 ions. Electrode use the data book of page 15. So when you work out for sulfur dioxide, you will like why it is suitable. It will reduce the iron 3 ions into iron 2 using a page 15. This was page 17. So this one we have 0.44, because this acid was used here. As you can see, H2S3, sulfur dioxide aqueous, which is H2S3. So H2S3, this one is H2S3, that is 0.44. And for converting, because the electrode potential for the conversion of iron 3 to iron 2, like if you want to convert and all our reductions are there. So that was conversion of iron 3 gain electron turned into iron 2, that was 1.51. So you can still see that this substance will be reduced because higher electrode potential, so this will be reduced, so this will oxidize. So when electrode potential of the aqueous sulfur dioxide or sulfur dioxide is smaller than electrode potential of iron 3, so this will be reduced and the sulfur dioxide will be oxidized. So just use the electrode potential mentioned, like the cell volt, or you can also calculate a cell voltage by the same reduction minus oxidation. So if it is reduction, it is 1.51 minus oxidation 0.40. Again, you will get a positive answer. I think iron 2 to iron 3 was 0.77, not 1.5. I guess it was 0.77. Yeah. So the same idea, 0.77 minus 0.40. So this will give us iron 3. Yeah. The same idea, it will give a positive electrode potential, sulfur dioxide. Yeah, so this conversion is giving us a positive answer. H2S3 aqueous is there, 0.44, and for iron 3 to iron 2, that was 0.77. So when you subtract, you'll get a positive answer, 0.77. When you subtract, you'll get a positive answer. That's why this will be feasible. Then calculate the percentage by mass of iron 3 in a sample. So what we'll do, I will just explain the method. I'll not calculate. So you will have the volume and concentration. This will give you the moles of manganate. From moles of manganate, you will find the moles of iron 2. How to work out the moles of iron 2? The main equation is given in the beginning. So moles of iron 2 or iron 3, it won't make difference. So you got the moles of iron, you got the moles of iron 2 here. The ratio is 1:5:1. So you'll get the moles of iron 2. After getting a moles of iron 2, these are the moles in 25 cm cube. But original volume was 250 cm cube. So in 250 cm cube, it will be 10 times. So you'll get the total moles of iron 2. And total moles of iron 2 will be same as moles of iron 3 because they have the same ratio. After getting the moles multiplied by molar mass of iron 3 sulfate, you will get the mass of iron 3 sulfate used in the experiment, or mass of iron 3 oxide. So after getting a moles of iron 3, multiply by molar mass, because 1 mole of iron 3 give 1 mole of iron 3 oxide. So multiply by molar mass, you will get the mass in gram of iron 3 oxide. Then iron 2 sulfate can be oxidized by dichromate in acidic condition. Use the half equation oxidation of iron reduce and reduction of dichromate ion. Write an overall equation. So the same way as we did in the previous question, like we have the equation for iron 3 and iron 2, which is 0.77, and the dichromate is also there. So it will be simply the reduction minus oxidation. You can write the half equation and then combine them together. Use the half equation to write the overall equation. So first, the conversion, like example, if Cr2O7 dichromate ion, 14 protons are there, 6 electrons, give 2 Cr plus 3 plus 7 H2O. And then iron 2 converted into iron 3 by electron, and just multiply this by 6 and add the two equations, you'll get the answer. Suggests a practical reason why potassium manganate is preferred to potassium dichromate, because potassium manganate changes from purple to colorless, but potassium dichromate show a transition of a color, like from orange to green, or from yellow to green. So which is like color transition, it's difficult to identify how much iron has reacted as compared to color disappear. Like from, if potassium manganate, it will be colorless to purple, but in potassium dichromate, it is from orange to green, or from yellow, if it is in acidic condition, yellow to green.